that can be, it's not an obstacle, but it's something you have to develop as an ability to basically be able to cooperate and work as a team member. Now, that doesn't mean there isn't still some competition, and it's sort of there's always a tension between the competition and working as a team member. And the competition even now comes within the team. Which member of the team gets the best idea, and that the team will follow. And that's where a good part of the competition comes out. But once you get a good idea, you get together and you work on it. And the reason that happens is because the projects are so large, and the instrumentation is so complex, there is no one or two people who can do it. You need large teams to do it. It's like, very often like industrial projects. You go to some industrial lab, and you have a complicated project, you have a team, and they have to work together to make it work. That's also occurring in science, at least in energy physics, and I suspect in other areas.
Thank you so much. My question for you is, what advice will you give to a young student who wants to become an astrophysics?
What do you recommend as a young student who wants to become a physicist?
Oh, I think the thing is to do a lot of reading, try to understand what it's all about, and make sure the passion is there. I always say to students, they always ask me, what should I do for my career? And I tell them, follow your passion. Don't do anything that you will dislike in the future. You spend more of your time in your vocation than almost anything else you do. And if you don't get up in the morning and feel a great joy at going to work, you're missing out on something. So I say to students, follow your passion. Don't worry about the so-called economic consequences. If you follow your passion, you'll be very good in what you do, and there'll always be a place for you. On the other hand, if you don't follow your passion, it may not be so good because you don't want to make the investment in it, and and you also have an unpleasant existence. So, for young people who want to pursue physics, I think it's important to do a lot of reading, understand that they really wanted to do it, and try to think about what areas of physics they would be passionate about.
Thank you.
I have a question about science. I'd like to know if you think that science is now united. I mean, Descartes, il a dit que Descartes, he pretended to have a united science. Do you think that the science is really united enough? I'm talking about, I can speak about physics, and I can really link it with, for example, the psychology or something like that.
Well, you mean interdisciplinary work, how to relate the sciences to one another?
Yeah, work in the different areas of the science working together. Do you think that they're working together right now?
Oh yes, it's starting to be very prominent. I mean, for example, I'm helping develop a new university in Okinawa, which has just opened up. And it's a graduate research university, and the whole idea is to develop a structure to encourage and nurture interdisciplinary work. And we have physicists and mathematicians there, and life scientists, chemists, and the idea is for them to do whatever they want, but by bringing them together, we hope that they will work together on various problems. And for example, to help develop such a structure, this university has no academic departments. It just has laboratories where people work on projects. No academic departments. You can get courses in physics, and mathematics, chemistry, but there is no department. And it's working out very well. And there are certain problems in science which will absolutely require interdisciplinary work. One of the great mysteries in science today is how the brain works. And that, to get an understanding of how the brain really works, will take engineers, physicists, chemists, mathematicians, and life scientists all working together. And that's what's going on in the various institutes that study the brain. It's going on. And so there are some problems which absolutely require interdisciplinary work, and it is happening, and it will happen more and more in the future.
Okay, thank you.
Hi, nice to meet you. I'm a bioengineer student, and would you like to tell us your studying technique?
Your studying technique. What engineer are you?
Bioengineer.
Bioengineering. She would like to know what your studying technique is.
Oh, that's an interesting question. Well, you know, I guess what I try to do is try to, you know, if I learn something, I try to understand it as a whole rather than looking at little parts of it. And I find, at least in my mind, that once I understand it as a whole, how it fits into other things, I can understand it much better, and I really do understand it more deeply. If I try to take little pieces and understand them alone, very often I have difficulty. So I guess my study technique is to try to read things over, read them over and over again, trying to go through the reasoning, and then trying to understand the entire structure in which this knowledge fits in. And that I find very useful. But I'm not sure it's useful for everybody. I mean, I think different people have different modes of learning. And I think what you have to do is find the mode of learning that you are most comfortable with and which is most effective for you. And so I wouldn't want to prescribe that necessarily for everybody.
Okay, thank you.
Here.
In some of your answers, you define yourself as an experiment. Can you describe the way of experimental physicist and what is the most important of that part of development of scientists, and which is the principal difference with theoretical physicists or physicists?
Yes. Okay. In a certain sense, one has to be careful when one thinks about experimental physics. An experimental physicist in general doesn't only do experiments. A good experimental physicist will think of what is relevant and why it's relevant and what is possible. Let me give you an example which happened to me, and then you'll see what I mean. You know, I was Fermi's last student, and Enrico Fermi was an absolute genius. He could take any physical problem and, in very short order, write down one or two equations, rather simple equations, and come to an answer which is probably close to the correct answer. The man understood physics so deeply that he could do that. The answers were never exact. He could do exact calculus. He was also a fantastic theorist in his younger days. But near the end of his career, he decided that only great progress would be made in experimental physics at that point. More had to be understood before one could develop theories, and he was absolutely correct. And so he himself went from theory to experiment. And he spent all his time in experiment, although he did theoretical calculations on the side. So I observed this, and when we were starting our experiment looking at the proton, so I said, look, we were preparing this experiment. I don't have much time to work on it. developing all this equipment and building things, I went to some theorists and I asked the theorists to make it, if we take what I call the current picture of the proton, if we scatter electrons from it, what will we expect to see? Because you have to have some template. You're going to go into some totally unknown area. You have to get some measure of what you're actually seeing. So I went to a couple of theorists, and they said, absolutely not. It's too messy. It would just be junk. And so I decided, I said to myself, what would Enrico Fermi do? And I'm not anywhere as smart as Enrico Fermi, so I'm not comparing myself to Enrico Fermi. But he would sit down and make an approximation about what to expect. And I sat down and I did exactly that. And when we started doing the measurements, so we started getting results. So we had a template to compare. So initially, the results, we were looking at the scatter results were a factor of 2 greater than what I calculated. Yeah, it's an approximate thing. What's so bad? Don't get excited about that. We continue. We went up to change the kinematics with a higher, so-called higher momentum pressure, and the results turned out to be 5 times bigger, and then 10 times bigger, then 100 times bigger, and then 1,000 times bigger. And at that point, we knew we were onto some new physics. But if we didn't have that template, we would never know that. And so, if you're an experimental physicist, you have to know roughly what you expect to measure if you're going to do anything significant. So experimental physicists have to be what I call approximate theorists. They really want to do something. Now, a theorist